right, Isabel, thank you very much. That was a beautiful introduction. Saves me some time in telling stories about myself as well, which is good, I think. This talk is called Lost in Space because that's a little how I feel right now. When we applied for the talk as well, we thought that the project would be done at this time, but we encountered so much potential that we decided to prolong the project until December even. As I go through the talk, maybe you'll see why this is. Some things might be a little complex, but I try to narrow it down enough for everyone to follow. So, as Isabel just mentioned, I'm a graphic designer and a touch designer enthusiast. I really grew in love with the community in Berlin 2 years ago, which was this was a presentation I did on a project not worth mentioning related to the project I'm currently doing. But I saw just the sheer power of the community. It's real nice. In art, most people really shout loud to be heard, and in coding, people collaborate because it's difficult to talk to machines. So this is fantastic. So where did this all start? This is really cool. It's a community thing. It started as a blog post on derivative. Isabel wrote it because Romano, the director of GRANTECAN, who will be speaking in a bit as well, found out about TouchDesigner and saw all of its potential to visualize science. So if you were reading this at the right time in the right moment, and you would have emailed to Romano, there's a high chance you could have collaborated in the project. For those who are too late, there might be something at the end to still continue this. A mailing list was composed. I think it was 15 people at first, and we started sending back and forth innovative ideas on how we could elaborate on everything space, but we had to make it concrete in the end. So what ended up happening is that someone had to have the horrible job of going to La Palma and staying there for around half a year. Yeah, I'm gonna make you jealous now, I'm sorry. This is La Palma. It's quite a small island. I think it's beyond civilization. It's on the same latitude as the Western Sahara, but it's a Spanish island. This is the view from my house there. We have sheep. I think it's best to leave the introduction of the telescope to the one who is currently running it. I mean, that would be nice. On the left, you see Romano Corradi. He's the director of GRANTECAN, and he's a brilliant guy. He's quite intellectual, and it has been a blast to learn from him. He tried to push 10 years of education that he had in 2 months for me, so that was a bit of brain damage. Romano.
Good morning. I will speak only 2 minutes because he's the art director of the story, so I just give a very short introduction. But first, I have to say that we are delighted, and at the same time, we are immensely grateful for the interest that the community has shown in our installation, in our project, and grateful for the help that the TouchDesigner team is providing us for the project. I will tell you basically. You see a little bit of, well, you don't see anything here. Here is the telescope, so it will be something what we do. We are a telescope. What we really do, every night, every clear night of the year, we look upstairs, upward with the telescope, trying to improve our knowledge of the universe. This is all what we do, and is a beautiful, but also is a tremendous challenge. Yeah, it's true, this is the largest telescope of the world, so in principle we should be able to go as far as the limits of the observable universe, and this is the goal, but the goal is a very difficult challenge. It's a very difficult challenge because the only thing we have is a few particles of light, photons, a few photons coming from very far away galaxies. We have to understand the universe only with very few photons. I was writing this morning, making some numbers. From the sun, every square meter on the Earth, we receive every second about 1 followed by 20 zeros photons. Yeah, okay. In the universe, we are, when that's finished, I will show you one of the deepest images we are getting with the telescope. We receive a few photons per seconds, or even less, in some cases, few photons or one photon every 2-3 minutes from the first galaxies that formed, that we can look, really try to investigate, because we are going far away in space, as you know, yeah? We are going backward in time. So if we move, this is an image, and here you see the power, but also the difficulties of things. This is the telescope is a large collecting area, 10-meter size. But in order to get this image, we had to expose for 110 hours. So, and that's, you see, 10 nights of the telescope or more to get that. But then you see, all what you see there are galaxies. These are not stars. They are galaxies, and the thinnest and the smaller points are galaxies which are really close to the limit, to the edge of the universe. So in one image, this is a tiny piece of the sky. Yeah, it's 1/10 of a degree, very small. You have several thousands of very far away galaxies. And in our job is very difficult, because from that we have to understand the physics, how this started. So not only we have to try to get those images, but as Jakob will show you, we have to analyze these photons as much as we can, which is basically to try to measure their energy also, which is their wavelength, or in other words, their color. So it's, I think, is a very difficult challenge, but very beautiful. And what is the scope of all this is to try to communicate to people in a way that is modern and that attracts everybody. And this is what Jakob is helping us to do, and the community is also helping us to do. So I just leave the word to you, please.
Thank you. All right, that was a beautiful explanation. Well, yeah, so the thing is actually really big. 10.6 meters in diameter. 10.4, thank you. And right now they are running in a technical corridor. They're running a video that you see behind me to explain the telescope. And this is, although it's a fantastic video, can be done better. So this is what we're trying to do right now. This needs a moment of attention, because GRANTECAN is a public institution, so there was very, very little funding available. And all of the people that you see here have contributed out of the kindness of their hearts and made many, many hours to contribute to this great project. I have to go over a few of them. You see the TouchDesigner team on top. Roy Gerritsen and Tim Gerritsen took me in as one of their own when I started this project, because it was so humongous, astronomical, you could say, that I was a bit scared of the project. So I approached them because they were really good and solid TouchDesigner guys. So they took me in and said, well, we'll help you create this immersion. After that, we see a couple of great artists varying from what they made is brilliant work. It's great to see their patches and to go through them. I'll show you some of that later. And the people of the telescope have been helping. The video you just saw was made by Veronica Pardel, who jumped in last minute to compose all the footage that we have, because it's such a beautiful thing. And a really big shout out to everyone at Derivative. I know Rob is not on there yet, but he created something that I will explain a little later as well. Working with so many people over a distance was, this is Mattia that you see here, was quite, that's Riccardo is an astronomer, was quite a challenge as well. We brought artists in connection with astronomers to explain the teeny tiny bits of science. Who you see here is Augustin to the left. He shows us with a regular telescope, not an electronical one, to show how space looks. This was a very, very interesting thing to see. But it also means that you get the work of all these people, and that varies from fascinating to brilliant solutions to working patches on 60 frames per second to working patches on 2 frames a second to genius patches that are difficult to change. But I mean, it has been a blast looking inside of the heads of these great artists, because truly that's what they are. I started this project with Tim and Roy Gerritsen in Amsterdam, and they decided to help me on the framework to set it all up. So we didn't know too much space yet, but we knew how to projection map. Richard Burns composed a timeline module that we still have to integrate. But the problem is, if you start creating all your own tools, it becomes sort of fractal. I mean, you can spend 2 weeks on a button. I was working for the telescope, 2 weeks on a button. It hurt my feelings a bit to say this as well. So you could lose a lot of time like that. And another problem is, which Roy mentioned to me very early on, he said, this is going to be the best product you can deliver now. After this, you're going to do better. That sucks. I was like, this is the biggest telescope, and then I'm just going to ruin it. So we'll get back to this. I made it a bit more complicated than it could have been. I decided to go for real data. We had a meeting early when I arrived, and we decided to check out if we can incorporate some real data in there. But the problem was I didn't really know how real data looked like. I first had to go through an astronomy course. One of the snapshots from the current videos, what you see here, is very CGI, right? I mean, this is not real data. So, okay, what is real data? Well, they shoot beautiful, beautiful pictures. This is broadband mostly, and I think indivisible. These are images that are color composed, so there's already a step of editing, an artistic impression in here, right? So it's real, but the colors, you can debate on those. It's quite difficult to get those accurate. So what is the real data? Okay, so you can maybe understand my surprise when I saw this. And if you go further, you even see an artifact on the left, and you see the 2 CCDs of Osiris. You see a flat, which is basically overexposure to check for corrections that they have to make on the telescope on at least a daily basis. So this is more interesting data. This is actually spectroscopy, so what the hell we're looking at, I'm going to explain some more. This is the reading out of the CCDs in a particular speed, the alterations of the grism, which dissects the light coming in, the different filters in which they can shoot. Oh, and if you thought that was complex, that was one of the instruments they have, and there was just very, very little information about it, so you could maybe understand that we were a bit overwhelmed when we really dove into this. Oh, there's more. We have blueprints of the telescope. I'm wearing a shirt. It's just cool. So we had to work with it. They have every nut and bolt, every machine, everything digital. They have the observing screens from this is actually the control room up in the telescope. So what we ended up doing is deciding on a couple of topics that we wanted to cover. Basically from 1 until 8, the rest is just folder structure. So depth, spectroscopy, infrared, the effects of gravity on light, and others. But even those subjects are, again, divided. So it's, again, fractal. This is the corridor. It's a lot bigger in real life than it looks here because the pathway is 5 meters broad. I had to pick a color for the paint for the floor. And I just picked something with paint. I thought, like, this is a good color. I don't want too much light pollution. Apparently, this has to go through the company that does the paint for SpaceX, so it's a very long process as well. They were starting last week. Besides that, I thought it would be really cool to have a real-time pipeline to the telescope. So what do we need to do? We need to integrate the real data, which is in the format of FITS files, into TouchDesigner. So here, this was my first try. I spent 2 weeks on this, also with a lot of help from Tim. And what we did is we converted the FITS files through Python AstroPy module to DDS, but we had a lot of problems retaining the depth, and it's very important because if you have only gray values to watch, the detail, the resolution of that is very important, because if you're doing science and your gray values are wrong, you're making the wrong calculations. Then you had to load these DDS files and normalize them, which was also a problem I fortunately had help with. And then we received something fantastic. I'm really, really super grateful for this. Isabel and Greg are both very interested in space, so I was chatting with Isabel since the start of this project, and she found out that we had some problems with the FITS files, so she asked the team for help. Well, what did we receive? We received FITS integration for TouchDesigner, just in a movie file in top. So this is this is fantastic. I could have cried, and if I go on too long, I will do it now. So this is brilliant. So this means all astronomers around the world can now integrate their data into TouchDesigner. This is, well, for me, this is, yeah, this is beautiful. Thank you. Yeah, derivative, good job. Rob worked on this, so Rob, thank you. And it was also great because it contains some examples made by Greg, which is just seeing the master play with his own tools. Like, wow, that's a way to wake up. So for audio, I'm going to play some now. Let's see how, do we have some sound in here? Oh, we don't have a sound. That's sad. Is there an extra cord for the sound below here? Maybe we can check that meanwhile, while I continue. This was the audio board. I don't regularly make these, so this is basically just an orbit of 2 stars around, or an exoplanet in orbit. And I thought it would be really, okay, this should work. We can continue from here, though. The audio is made by Rodrigo Tamariz, who, with a real orchestra, composed the abstractions of sound in space for us, which was... I've never really worked with sound for an installation that I had to do that just became one of my favorite songs, so I'll send it to everyone somewhere online. I've just been listening to it. It's like 10 minutes of beautiful composed music that is going to be narrated over. And what you meanwhile see... Yeah, it looks like it. I think it's the, well, I could try this one. Yeah, somehow it doesn't stick. But what you see behind me is we, of course, had to deal with visualizing science, and some part you want to be more artistic, some part you want to be more scientifical, or you have to be. What you see behind me is very artistic. It's just an impression of how photons accumulate and eventually show the deepest image of space ever taken. This is going to be projected on 2 sides wall, 1 front wall that you just saw. So that was a cool sketch to make. I mean, we continued on this principle a bit. We have, this is inside of the Milky Way, so it's much closer. These are stars that accumulate, and basically we did some vertices displacement in this case, vertices counting actually. And what you start to see now are all stars in the Milky Way, which is a fabulous sight to see. So this is the real data, not color composed. It gets a bit more scientifical. Then here, we look into infrared, which is a very big part of what GRANTECAN does, is actually look in the invisible spectrum, the light that we cannot perceive. And what you see here is the detail that reveals. It's just absolutely astonishing sometimes, just like how much light there is behind the clouds, how much emission. From there, this one I really like because it shows you quite a lot of the process. Maybe we have some time to take a look at this, because this shows you the data acquisition, all of its phases. What you see now is the bias, which is just noise created by the machines surrounding the CCD. From there it goes to a flat, to an observation where you still see the 2 CCDs separate, to eventually the whole image, where on the right you see infrared that we used as a height map. Because we already had the colors from one instrument, but we had another instrument which looked in the infrared, so the invisible. So we have multiple data sets to combine together, and there's, of course, a couple ways to do this. This is one of them. On the left, you see something that is, well, actually made by Derivative. It's a waveform monitor that we adjusted. So thank you very much. It was very useful in this project. But it's also a very nice thing to show, because this is something that astronomers use a lot, is actually looking at the graphs and the light intensity of different color spectrums. Let's just watch it one more time, because maybe it went quick. So you have the bias. This is the flat, which is just the sky, and you see on the left, you see the waves changing with the intensity. I think this is just a cut from the middle. But to me as an artist, even the data that to the scientist is not relevant, like the bias, for me is beautiful. I mean, I was so excited. There was a board meeting for user groups was the best astronomers in the world that used the telescope, came there. I was a part of that meeting. And there was something wrong with one of the instruments, and I was just amazed by the beauty of the data while everyone was focusing on the problem. This is a module made by Mattia Diomedi. I think it explains itself, really. It's just how different wavelengths have different colors, and together they form white, right? All colors together if you overcompose them, which in this case is a feedback loop. We use them a lot. Composes white. And the cool thing is, if you start changing amplitude in that, this doesn't convey much of a scientific message, but it does an artistic one, which is it's just geometry. Yeah, so this is just cool to watch. So I had to keep it in there. This is the galaxy we just saw as well as M51. All the filters just combining over each other. So this is infrared, this is the visible, all connected to each other. And it shows you what different things appear in the scaling of these images. Let me see, we might get a bit more technical from here. Yeah, so this one is an important one. This is spectroscopy. What you see right now, maybe I'll just do it pause and play, otherwise it takes a while. What you see is an acquisition image. This is just a picture it takes, and the telescope takes, and you see some stars. From there, they select the star that they really want to observe. So they put like a mask over it, and then what they do is through spectroscopy, which is dissecting light, is basically a prism, right? A rainbow, white light into a rainbow, so the reverse of the light waves that we currently saw. So they have this one slit that out of it comes a whole bunch of information because it's separated by wavelengths, so you get different colors, which is the data that you see here. These colors are not accurate scientifically, but they're meant to educate and clarify some of this. So what you see here is all the vertical lines are emission lines. They are in every position. The y-axis is the position of the objects. The sky emits at certain frequencies, emits light. So you see all of these lines. But actually the object we're looking at is the one horizontal line right there. Now what you have to do is you have to subtract all the emission lines from this one line to get a clear view of what actually the spectrum of the star is, which in this case is this. So this is the real data. It's basically a one-dimensional array again. So it's just one line of black and white intensity, or gray intensity. And if you compose that in a graph, you see what we have in the middle, which is interesting. They actually start looking for these dips that tell them interesting stuff, like could there be oxygen on a planet, yes or no? And this is a star, so it's different, but. So this one was a difficult one to get good because you want to have it look aesthetically nice and you want to have it explain something. Now in the final installation we'll be using narration over this, so just like I'm guiding you through all of this, there will someone be guiding you there. But what I thought was really important, that we did not give up on the real data. I followed one of the astronomy groups that visited the telescope, and they were real astronomers, and what they got to see now was a little below their expertise. So, and I thought it was such a shame because there's like 10,000 visitors yearly coming to GRANTECAN to view what they do. And I thought it's the biggest shame to leave the professionals out. I mean, yes, you got to have everyone along, but let's try it without compromise. This one's really awesome. It's made by Richard Burns. He did a really good technical job at stabilizing this. This is 6,000 images of a binary star system, which is the star in the middle. And what you'll see is when they go in eclipse, so one is in front of the other, there's actually a dip in the color. There's a dip in the emission that they're watching. So this is he did a fantastic job because he really wanted something technical, so I gave him one of the worst, and he figured it out quite quickly, which was brilliant to see. So you can actually see the two stars optical, which is cool. So you're not only watching graphs, they're there to amplify, but you can actually see the stars dimming and changing color. Now this is one of my favorites, and until last week I got the data completely wrong. What you see here is again a one-dimensional array, which shows you a lot. You see a lot of different vertical lines, which I think are really cool if they revolve around you. These are emission lines from different places, could be atmospherical. And actually the data that we're searching for is so far zoomed in that you wouldn't notice it at first, which is the two black lines that you see here. This again, in this case, there are absorption lines, so light can be emitted or it can be absorbed. And if we play this again, you see them merging and separating, which is again the rotation of these binary stars. And these binary stars revolve around each other at 800,000 kilometers an hour. It's really something. And here you see the graph. So this is actually the data. The two peaks in the bottom are the two stars separated. And then when we merge them together, you see one peak. So this is the data that the scientists work with, but we had to clarify this a little more. So from here, we take it to something that you could call more CGI, although we did it in, I think, a good manner, because the shapes that you see here are actually ran by an astronomy simulation. So the vertices that I received from an astronomer were actually composed in a simulation. The colors we used all throughout this experiment, all throughout this module, to explain the Doppler effect, which is that if a star or if any light source moves towards you, it is bluer, and if something moves away from you, it's redder. It's the same as with the sound of an airplane. So the Doppler effect goes in multiple ways. Yeah, this was one of my favorite. Before I totally had the wrong lines. Now this is one made by Jeff Smith, and this is absolutely fantastic because I gave him the blueprints of the telescope and let him play with it. And he's originally an illustrator, so he went all out on it. And what he did is, this is a top view of the mirrors and the actual segments, and he nailed it down to very, very high accuracy on what way he visualizes this. And it's beautiful in the same way. But the cool thing is, again, you're playing with the real data. So you see here all the individual segments. It's, I think, 36 segments make the total mirror. They replace one every so often because it gets dusty or damaged. Let me see. Oh, this is a bonus one. This is one of my favorites. This was impossible without the integration of FITS because the resolution was too low. I had 8 and 16-bit images, so we had just too low of a resolution. What you see is M11. It's a star cluster. And how can I make this example? If you're inside of a forest and you only see the trees nearby, but you want to see the whole age of the forest, that's pretty difficult, right? So this is the same thing, but then for a star cluster. We have only this time in observation when we can really see it. But we want to know more about it, about its history, about how old or how strong some of those stars are, or how big or how far away. So it's one of the first shaders I computed with also a lot of help again from Tim. What you do is if you separate the blue and red intensity from each other, and later you do that on the y-axis, and on the z-axis what you do is you just do the general intensity. You get something that, one, looks cool, but two, is actually very scientific, because this is an H&R diagram, which tells you the ages of the different stars. We can still improve some on this, but I think it's fascinating to watch. Even now, I keep gazing at it. It's crazy that you just, from a broadband image, so not even a very refined spectrum, you can get all of this data. You just need a color image. You can do it through Google search and play with some. So these are the data sets that we have. Now we should be able to go one forward. Somehow it doesn't. Let me check. We have seen all this. The beauty of last-minute touch patches, right? Maybe I can just change this manually now. Yeah, it should work. Okay, cool. We have some really cool announcement to make that I'm super stoked about. I mean, this is fantastic. We started this project, we saw its potential, but people around us started seeing the same. They were like, what, this is cool. Oh, I have this idea, And some people said, well, isn't it also cool, just besides the editorial thing that we can do, is it just cool to have artists play with this stuff, right? I mean, it's a gold mine of data. So I chatted with Rafik Anadol, who made these, he made this from Mars Curiosity pictures, I believe, with his AI gen transfers, Rafik. He wants to kick off something that he initiated. He said, why don't we do a residency inside of the telescope? I mean, isn't that a cool place to host an exhibit as part of the installation? So first you run the installation, people see the telescope, they come back, and we have artists that run one of their projects for a month. So we got that going, and behind him you see one of the machine arms that he acquired recently, and we're also thinking about using some of his AI stuff together with the blueprints to print like little models of the telescope or something. I think that would be really cool as well. But I don't think Rafik uses TouchDesigner yet. And we can't have this without a TouchDesigner. And one of my favorite TouchDesigners, which I'm really looking up towards always, is Matthew Reagan. And we invited him as well. And he was very keen to get started with us on this. So we have the first two artists set, but of course everyone here is welcome to just look into playing with the data. I can send you everything. There's a lot of it is actually open source, is already publicly available. You can now load it in TouchDesigner, start playing. If you have questions, hop along. I think this project we will run, well, Romano already said, like you can start thinking in the long term, like what do you want to do this year, next year, you know, what we want to do with this. So this is really cool. We of course know Matthew from, I mean, who hasn't watched the video of his? Okay, yeah, see? That's actually good, it's better than, yeah. So I think this is a fantastic opportunity and a fantastic chance. Thank you all for listening, and if there's like any questions, feel free to... Oh, and the super cool type overlay that you just saw is made by Jason. It was brilliant. It was a big help as well. I just started pulling people at the end of the project that was like, this is so cool, we need more. And now it got so complex that we need to narrow it down. But yeah.
Check. Thank you very, very much, Jakob and Romano. And the line starts here. No, but does anybody have questions for Jakob? I
see one there
in the back. Yes.
Questions are good, guys.
Where can we find this open source?
That's a very good question. I hope my browser remembers it, because I don't know, I remember the URL, but I can send it there. It's archive something. Romano, you should know this. It is the GTC archive.
Romano.
I have a lot of FTP stuff
so
here.
All the major telescopes in the world, and with this I include the Hubble Space Telescope, for instance, or the telescopes in Chile, or GTC, our telescope, GRANTECAN, they all have a public archive. So usually scientists are given a proprietary period of 1 year that nobody can look at the data, but after 1 year they become public. So every telescope has its own archive. You can go there, dig, well, of course you have to know something basic of astronomy, so you know what you want to look at. If you know, for instance, a certain galaxy, you can, even there are some virtual observatories where you put the name of the galaxy, you get a list of images that you can get out of the archives. So it's just a matter of navigating a little bit in internet, and you can get real images from all the big observatories in the world.
I'll help you find it in a bit. And what is good to know is that the astronomy, well, just the naming conventions for all these objects, damn, that's confusing. is like UGC 1312, you know, like, oh yeah, that's that one. And of course the astronomers know, but I mean, as an artist, you have no clue where to start.
Have you thought of renaming any?
Well, I think derivative would be a good one.
Just
I mean,
kidding.
we could have a cluster called Greg, we could have a galaxy called Isabel.
I'm down with that. Okay, questions? Rui?
Hi, thank you so much for the explanation. One question, I don't know, it's for you or for Romano. What's an emotional arc? It's for him? Okay.
Oh, you mean
what's an emotional arc?
Oh, you mean from the audio board?
Yeah.
Well, actually, okay, this is the fun thing. So the orchestra asked me to compose an audio board, right? Because how the hell do they know what to do? I've never made an audio board this specific. So what I decided to do is look within astronomy and find, well, in this case it was a cycle of two objects orbiting each other which caused an eclipse. And I thought this would be a very beautiful, abstract representation of what the audio could sound like. But it leaves a lot open to interpretation. So what I meant with the emotional arc is generally in movies what you have, or in the Walt Disney stuff at least, you have that something starts slow, you start to know the character, you know, it's nice, and then something goes bad, and then it goes all good, or, you know. So this was a bit what you had as well in that graph.
Okay, thank you.
But I just suck at the audio board, that was the...
So are there any social media places where you're talking about, or you will talk about, TouchDesigner related uses of uses of TouchDesigner in astronomy that you're right now? I think up to now you've had kind of like private group producing work. So how about anything more public? That
I think that's a really good idea. I've been thinking about this too, but I don't know how to initiate it yet. I thought at least about growing out the Slack with the artists we invite, because we currently run it within Slack, but I think it would be cool. Maybe we could do something on the new forum. I don't know how things are getting along on your side.
Yeah, no, it'll be good. And also, not just the raw data, but if you were thinking of putting out talks files with the original data processed with a lot of the ideas embedded, sort of what the ideas what you presented here.
Hell yeah.
Putting that out in public so other people can take that already pre-filtered stuff and then make stuff out of it.
Yeah.
Hey, derivative, I think, is sort of the idea.
I think that is a brilliant idea, and of course, I mean, there's some data in here that we cannot share. So maybe you have a picture of it, but I mean, it's still classified. But most data is public, so why not open source this? I think this is also what the Touch community is about. I mean, not keeping knowledge to yourself, but just sharing these, because life's too short, right?
Yeah. Well, at the Berlin Summit last year, we announced that we were getting a new website. And at this summit, we're announcing that we're still getting a new website. But on this new website would be a great place to have a whole GTC, TouchDesigner, you know, blog, right? Your own, right? You can share assets, brainstorm. Yeah.
Twofold question. One, what was the process like in developing the visuals? Did you kind of have an end idea of what the visual was supposed to look like, or was it a lot of improvisation and play? And then secondly, related to that, in the process of creating artwork from the data, what steps did you take to make sure that you were still kind of remaining true to the science and to the data, even as you were artifying it?
Well, they're both good questions, and I think I can answer them in the same answer. The beauty about TouchDesigner, this is something, a part of the presentation I forgot, thank you for reminding me. Well, it's basically what brought us together is TouchDesigner as a language. So even though not everyone on the team spoke English, we still communicated and built stuff together, which is, I think, is really fascinating. And the beauty about TouchDesigner is that you're so quick at visualizing ideas that you should see some of my first sketches. It's horrendous. It's scientifically super wrong. but then an astronomer could directly react to this, which speeded up the process tremendously. You just go with the painting and you say like, well, is this correct? No, what? A star isn't that size. It's an exoplanet, or it's like, so that works really well. But it started just out as play, and also because it's such a broad topic that you just have to make. And I think the thing that saved us is just start making very, very quickly and refining. And yeah, you tend to want to make more beautiful things, and the scientists just want an explanation. So that is sometimes where you have to reach consensus. Yeah. You're welcome.
More questions?
One behind you, Jason.
Howdy.
Howdy, Jason.
So maybe talk more about the header data and how maybe like trying to understand. I try to jump on this project like very late in the game, and it's just such a deep dive to figure out what you're dealing with.
Yeah.
But the header data gives you some information that the tools we're using, if you can explain some of that, like direction and atmospheric pressure and all those things. So there's some other interesting information that might help you know what part of the sky they're in.
Yeah.
So stuff like that.
Yeah, no, this is actually true. Jason hopped in really, really late because we met late. And the funny thing is, I had this education on the spot, but all the other artists had no clue what they were dealing with, so that was a bit of a delay. And the header data that you saw overlaid on the images was actually the white text. If it's a bit bigger, you can read most of it. Has fascinating information about everything that constructs the picture. So one, of course, there's a date, there's an observing astronomer, there's the status of the CCDs, the configuration of the grism or the slits, the filters being used, the already steps taken afterwards. The cool thing about the header data is that you can include everything you want. So you can even include publications. So then it gets really, really technical. This is something that we still hope to see integrated into the Touch module, because Jason made a module using AstroPy, astronomy library in Python. I had to switch computers last minute, so I couldn't really dive into that, which is sad. But it's very useful just to have a filter with some of the things you're looking for. So with every image, you immediately see snap. This is what I'm looking at, right? So yeah, does that answer your question slightly? No, yes. People know there's even more embedded. Yeah, way more. This topic is too deep. Yeah.
Okay, I think we have time for one more question.
Okay, cool. Maybe I can pop up some header data on the other screen meanwhile.
Yeah.
That would be nice. The astronomy tool that they use generally is DS9. Well, there's many, many tools. But one of them is DS9, and it's basically a FITS viewer, but already getting around that is, if you're not used to it, well, it's learning a new program. The only thing is you don't edit too much in this. Now, what is an interesting one to show? I think infrared, because we have M51, and I like that one. It's a nice galaxy. So right now we're gonna look at the this is the flats. No, let's not look at a flat, but let's look at a R filter. Yeah, I'm gonna try to move it there, but I first have to configure it here, or can I just say, I can duplicate, of course, that's better, right? So you guys can creepily see everything that I have on my computer. So this is, for instance, the data of the beautiful galaxy that you just saw. Beautiful, isn't it? So what already you have to do is look at the scaling. This is a very nice, Greg made a beautiful little network in Touch that he sent us as an example how to solve this problem. Because if you're not a mathematician or a scientist, it's quite complicated. But you see how much information there is in there. That's beautiful. Okay, but then you have the header, which is this. So there's super much information, not all of which is relevant, at least to an artist yet. But if you want to remake the picture, besides that, if you have a different date and the weather conditions are different, you could do it. So it's really cool. I mean, I still have to say I don't know everything about this, but
just for example, I think there's enough information in the
Yeah, yeah, yeah.
The
Yeah, yeah, yeah.
have some knowledge of how the telescope was positioned and what part of the sky.
Yes.
You know, stuff like that.
Yes. Yeah, yeah, yeah. You could definitely. There's too many things to cover. We really had to narrow it down. I mean, first thing I said to Romano is let's make a simulation of everything in space that we know in TouchDesigner. It was like, well, there's already tools for this, and they do it better, so let's not do that. So no, but you could, but you have to know a lot of variables. I mean, you can of course, search for these, but I mean, the weather conditions for one are very important. One cool thing is that we didn't explain in this talk is that there's 3 mirrors. So there's the big mirror, which is the primary mirror. You have a small mirror that reflects the light of that mirror back into a third mirror, which aims it at all the instruments around, which are basically bodies of your camera. So you're keeping the lens, changing the body. And the second mirror on top fluctuates, I think oscillates in 100 times a second. And it takes a picture of an empty part of the sky or a reference, and then it takes the picture of the object. And it does this so quickly so that you're able to subtract all this noise that you get from atmospheric turbulence, for instance. So these are things that are very time specific, but you can get super far. I mean, as I said, I mean, we have everything. We have everything of the telescope and the blueprint, so it's really cool.
Okay, thanks. I must say this is a pretty big step forward because the original goal of TouchDesigner was to appeal to artists making images, films, sculpture, sound, and so on. But being physicists way back, I also wanted to be a tool for scientists, and this is like pure scientists. And I see this as one of the first ways in which it's really flourished in the sciences. So I'm really quite happy to see this effort happen out of the blue. I didn't realize how much you did in such a short time. So yeah, like I said, I wanted in the end, TouchDesigner to appeal to engineers, scientists, artists, and people of all ages, oldest to the youngest. So that next part is that last part is next. Anyway, thanks a lot.
Thank you.